Now, all right. So we are going to, continue with lecture number 15. This is going to 16. Sorry, this is going to be about arch and gauge processes. Predominantly, we're going to start with arch processes. This is a specific type of processes. Just a moment. Okay, let me see. This is working. And here you go. All right. So before we start doing so, I want to consider the generalized concept, because the properties of the generalized process that you're about to see are also going to be true for the arch gauge type of processes. So, okay, so sorry guys, I just want to do the other, that's a slide, that's what I want to talk about. And then later we're going to talk about your next assignment. So I'm going to define this. This is a so-called stochastic volatility process. Now this definition is not an official one, because that involves, if you Google, let's say, stochastic volatility, then this is not what you're going to get. Let me basically tell you that one. But the issue is, I'm going to consider this generalized concept, which basically allows me to also consider the specific properties that only arch and gauge type of processes have. But apart from that, we're going to look at those as well. So let's say, again, so I'm calling this, I was not able to create a different name for that, which sounded, let's say, plausible. So a process is called a stochastic volatility process if it satisfies the following properties. Okay, so let's say we are going to look at the structure. So you have sigma, which is some sort of basically variance, or let's say standard deviation of some noise. And then you have a noise where the noise is going to be an IID noise this time, but with mean 0 and variance 1. So in this case, the variance of the process could relate to some sort of an expression where sigma is involved. So that's why basically the noise is going to be normalized, because as you see, the standard deviation sigma is going to be some sort of time-related issue, or it has some sort of time-related issue as well. Okay, so again, sigma is going to be also a stochastic process by itself, and that's it. Okay, so if you basically consider that, it must have just one property though. It must have a finite second moment. So the variance of the process is going to be finite. This is the only issue that I might be considering. But anything else is just basically, specification that I'm going to consider later on. So especially, the gauge type of processes. So again, the second moment needs to be finite. So in this case, the variance will be finite, as you will see, but that basically will address the second moment of the process, especially I'm talking about the process sigma. So whatever that stochastic process will be, this will basically just, the only requirement that I have for that is that its second moment is basically finite. Anything else can be neglected in this case. Okay, now the only issue that I will also add here to it is that the noise, the current observation of the noise does not depend on anything else, because the noises are uncorrelated. So they are IID, so basically the current observation doesn't depend on anything else. In particular, it doesn't depend on the stochastic process sigma, and it doesn't depend on its past. So this is basically the past of, sigma, which is basically the stochastic process, or sigma squared if you like to. It doesn't really matter, because the two are going to be equivalent. So if you know what sigma is, and you also know what the square of it is, and if you know what the square of that is, then you also know what sigma is going to be, because we assume that the process is not negative in that regard. Anyway, I forgot to mention that one. But again, so the process does not depend on, in particular, these expressions, namely let's say, sigma at time point t and its past. But on the other hand, let's say the volatility process can depend on past noises, okay? Not the current observation of the noise, because that is impossible, as you see. So again, what happens here with the noise at the current point in time does not relate to sigma at all, but the past of the noise, or past shocks, can have, let's say, to be more precise, past shocks can have impact on current observations of, let's say, the so-called volatility process. So this is basically what sigma would be. And that's it. Okay, so you need to understand that. So there is the possibility that sigma, the current observation of sigma in particular, does depend on past observations of the noise directly. That is going to be a possibility later on, but not, again, so I'm not going to talk about that. You'll see, basically you'll see what the generalization of the process will be. But that's, you know, a very simple structure, which I call stochastic volatility. Why? Because if I use this to, let's say, to capture dynamics of asset returns, for example, you will find that this expression sigma will relate to the volatility of the asset. All right, so that's basically the reason for that. Now, but I'm going to talk about some properties of this process. So that's going to be the following properties. These include the following, among others, especially the conditional expectation of the process. The conditional expectation of the process, given its past, that's basically what the structure would be. So if you have basically the current observation of time point t, and it does depend on its past, and you can take it out from the expectation operator, this is what it basically what it says, no matter what past observation that would be. And this is going to be 0 in this case. So the conditional expectation is 0. The unconditional expectation of the process is also going to be 0, by the way. Okay, so that is basic property that you have here. If the process is absolutely summable, so in addition, if this is going to be the case, then as you might see that the process is going to be a martingale difference sequence. Okay, so you might remember what the martingale difference sequence was. A martingale difference sequence was a process which had conditional probability of 0 and which was uncorrelated. And that is also what it's going to be. But again, I'm talking about that later on. Okay, so the variance of the process, as you will see, is going to be the expectation of sigma squared. This is what it's, you know, the general structure which is going to be about. So as you see, the standard deviation, of course, will be basically equal to the square root of this expression. So you might see if there is basically sigma squared involved, then sigma is going to be the standard deviation. So I'm not saying that is, but if, let's say, if this is equal to sigma squared by the end, okay, I mean, let's assume that this is going to be the case, then the standard deviation of the process is going to be sigma then. So that's something that you might be considering. All right, so therefore the name volatility. Okay, now I'm going to address basically also the covariance, because that is the only moment, let's say, that is missing. The covariance, as I mentioned before, is going to be 0, so the process is going to be autocorrelated, but not serially independent. So this is not going to be the case. I will explain that later on, okay? But any type of these stochastic processes are going to be serially uncorrelated, but they're not going to be serially independent, okay? So there is going to be dependency structure, but not in terms of its linear form, or let's say the past or future observations, whatever. Okay, so that is a very important issue, guys. And if you see that, okay, these are the moments in particular, I would like you to focus on those unconditional moments, let's say. And if the process is going to be the stationary one, that will only depend on the variance. So whenever you come up with a process like this, it's enough basically to consider its variance, because everything else is going to be time independent anyway. If the variance is time independent, then the process is going to be stationary. And if it's going to be stationary, then its variance is going to be time independent anyway by definition. So that means that the process is stationary if and only if, let's say, the variance of the process is time independent. So it's enough, so completely enough to focus on variances when it comes to arch and gauge processes, when you, let's say, for example, you would try to establish stationarity conditions wherever. So these are the things that are going to be involved, and I'm going to look at that a little bit closely. Anyways, so that's what it's going to be about. Okay, guys, is it clear? So again, if the process is stationary, this is due to the variance being time independent, of course, and that's the only issue that I might consider. So I will need to make sure the variance to be time independent. However, and that is not a contradiction, as I mentioned this basically last night, this is not a contradiction, because if you look carefully, I mean, okay, so I'm going to discuss these things. So I want to just basically illustrate these things, that these are true. Okay, how would you get the conditional mean of the process? Now, the conditional mean of the process, now first off, simply just plug it in. Okay, so that's where I'm going to start. Okay, so yt is equal to sigma times epsilon. That's simple as that. And then you might consider that the process is uncorrelated, right? I mean, of course, the current observation of the noise does not correlate with the process sigma at the current point of time. So the expectation of a product is going to be the product of the expectations. And that's what basically I'm going to use here. Okay, so the expectation of a product is going to be the product of the expectations. Both the conditional as well as the unconditional mean of the noise is going to be 0. So therefore, it doesn't depend on the past, all right? That's obvious. And I mean, it doesn't depend on anything. So again, it does not correlate with anything. It doesn't depend on the past of the process. Even let's say yt would be a simple autoregressive model. And then you will have that basically the unconditional mean of the process is going to be 0. That's it. Okay, so this is what it would be like. All right, now later on I'm going to also consider the unconditional mean, and the unconditional mean is basically obtained by the law of iterated expectations. Okay, so LI stands for an acronym for the law of iterated expectations. What does that mean? This means that the unconditional mean of a process, let's say, is going to be equal to the expectation of its conditional expectation. So I'm saying that the unconditional expectation of a random variable is simply equal to the expectation of its unconditional expectation. I think you considered that one in assignment 2, and I wanted to basically you to do this, so this is what it would be. And again, I'm going to make use of the fact that the law of iterated expectation is true, so the unconditional mean of the process is going to be equal to the expectation of the conditional mean. And since the conditional mean is going to be 0, then you'll have also that the unconditional mean is also 0. This is not rocket science, by the way. Okay, guys, so that's not difficult to see. Now I'm going to also consider the variance of the process. Usually when it comes to unconditional variances, I would consider the law of total variance, but since I don't have anything about the conditional variance of the process, I'm going to express this later on. I can bypass that relatively easily. So the variance of the process is simply just going to be the variance of sigma times epsilon. And what you use is basically, I mean, the variance is equal to the expectation of the squares, which is sigma, sorry guys, this is going to be sigma t squared times epsilon t squared minus the square of the expectation. Okay, so that is sigma t times epsilon t squared, but this is equal to 0 as we saw in the previous part because the unconditional expectation, right, is 0. So that means that the variance of the process is equal to the expectation of the square, right, or the mean of the squares basically, and that's what it is. Okay, then subtract the square of the mean, but that's since again, so subtracting the square of the mean, but the mean is going to be 0, so its square is also going to be 0. Anyway, so again, later on, the expectation of the product is the product of the expectations because the processes that are involved do not correlate with each other. In particular, the current observation of the noise has nothing to do with the current observation of sigma, as I mentioned before. Okay? The current observation of sigma can depend on past observation of the noise. That is possible. But since we have basically just the current observations here that are involved, and the current observation of the noise does not have, or not, it doesn't depend on anything actually. All right, now this is equal to 1 by definition. So that means that the unconditional variance is equal to the expectation of sigma squared. That's what it is. All right, so this is basically what it would be. Okay, why is the expectation of epsilon squared is equal to 1? Because the variance is. Okay, so the variance of epsilon is going to be equal to 1, or by definition, and since the expectation is 0, then this implies basically that the mean of the squares is going to be equal to 1 also. Okay, I think that should be clear by now. Anyways, okay, so that's the expression that you have for the unconditional variance, and the specific structure of the process will decide whether the process is going to be stationary or not. So whether you have basically something like that. as well. Okay, anyways, I'm going to also address the autocovariance, which is going to be 0, as I mentioned before. The autocovariance of the process is simply just the expectation of the products, because the minus the product of the expectation would be equal to 0. The expectation, or so that would be equal to the expectation of the process at time point t times the expectation of the process at time point t plus h, and both expressions are 0, as we saw. So that's what the basically what the autocovariance is going to be. Now, since again the current observation of the noise doesn't depend on anything, it does not correlate with the rest, so you can split it by that. Okay, you can take with you also other expressions, but you don't really need to. So I'm basically taking that with me, or even now that the current observation, because you have sigma time point t plus h. Sorry, I made a mistake. So sigma time point t plus h can depend on the current, because if, let's say, h is going to be greater than 0 without loss of generality, the future observation of sigma can depend on the current observation of the noise. I forgot. But the future observation of the noise does not depend on anything. So that's why the reason why I was splitting that here. Okay, expectation of the product of the two. So I'm talking about these two. So this is the first one, and that is the second one. All right. Multiplication is associative, so this is going to be the expectation of the products, and then the expectation of the products is the product of the expectations, because these things that are involved are uncorrelated. Keep in mind that future observation of the noise does not correlate with anything, okay, that is involved in here. All right, so that's why you can split it over here, and that is equal to 0, so that becomes 0 in total as well, and that's it. So there is no autocorrelation regarding the process, which is why it sounds very counterintuitive, as you will see, but there is going to be some dependency still. So we have dependency, but no autocorrelation. You need to understand this. That's an issue, and it indeed is counterintuitive. All right, okay, so that's what the autocorrelation was or is. Now I'm going to come to ARCH type of processes. ARCH is an acronym for Autoregressive Conditional Heteroscedasticity. Just skip it for a moment. I'm going to talk about that later on. But just for you to understand what the term heteroscedasticity means. Heteroscedasticity means that the variance, in particular of this process, all right, is time dependent, but it says if it's conditionally heteroscedastic, heteroscedastic is also the term that you might remember. If it's conditionally heteroscedastic, that this means that its conditional variance is going to be time dependent, even though the process is stationary. So that is where the name conditional heteroscedasticity would come from. Conditional heteroscedasticity refers to the conditional variance of the process, and if the conditional variance of the process is having some sort of time dependency, whatever, because it's going to be stochastic, by the way, but that's going to be the reason. So the conditional variance is going to be random, let's say, then it's called conditional heteroscedasticity. Then if it's autoregressive, then this means you have some sort of autoregressive structure involved regarding conditional heteroscedasticity. So this means, literally speaking, that the conditional variance of the process is going to be some sort of a stochastic process where some autoregressive structure is involved. That's it. Okay, you're going to see this from the definition, so I will illustrate that later on. Again, please remember ARCH is an acronym that is used in econometrics very often, and it stands for autoregressive conditional heteroscedasticity. All right, now a process, and there is an order of the processes too, is what is involved, because that is going to be referring to the autoregressive structure that the conditional variance of this process will have. Okay, so that has something to do with that one. Therefore, you also include an order, which is denoted by Q. So Q is some sort of, let's say, integer, positive integer, let's say 1, 2, 3, 4, stuff like that. Now, I'm going to address this again. So that looks like a stochastic volatility process. So that is a stochastic volatility process that I call it like that, because that has general properties. So every property that I mentioned before is also going to be true for ARCH-GARCH type of processes, but in addition, since these processes are going to be specific, that you'll see that as well. So what I'm talking about is the conditional expectation is 0. The unconditional expectation of the process is going to be 0. The variance of the process is going to be the expectation of sigma squared. And then the process is not going to be autocorrelated, so the covariance is going to be 0 as well. So these 4 types of properties that I mentioned before are also going to be true for the Arch-Gauge model, no matter what the structure of the process is going to look like. Bless you. All right, so again, the noise is an IID process with variance 1 in this case. It has variance 1. And then sigma is a stochastic process which have a finite second moment as well. Okay, so that is also going to be a necessity, but it's going to look like this. So you have, this is this type of autoregressive structure I was talking about. So if it says autoregressive with respect to the squares of the past, basically, of the process y itself. And that's what it's going to be. So the variance, the conditional variance, and as you will see, this is going to be the conditional variance. Okay, so you don't see this, all right, but you're going to see it. That is going to be the conditional variance. And since the conditional variance is going to be depending on time, in particular with respect to an autoregressive process of the squares of the current observation, of the squares of the past observation of the process itself, this means that the process, that's the reason why it's called autoregressive process. You raise your hand, sorry, you might have a question.
If we have a variable that has sometimes negative values,
it cannot have. So by definition, it's not going to be. Okay, so these parameters that are involved, all right? So these parameters that are involved guarantee basically that the process will not be negative. You could not get some sort of negative value for the key.
So we can use this model for interest rate.
I'm not particularly sure where interest rate, I'm not sure whether interest rate exhibits stochastic volatility. You can test this. There is a possibility for that. It's not very common, so I assume it's not in the empirical literature. It's not, relevant in that sense, but it's specifically used for returns as well. So if it's used for asset returns in particular, why not for interest rates? I can imagine there's going to be, let's say, some process here and there where you have stochastic volatility for interest rates, but that's not very common. So that's more like, the mean reverting type process that we'll have for interest rates. But again, it depends on the assumptions. Okay? So I'm not sure about that, to be honest. I haven't seen this quite often, if I recall it correctly. But I see this more often when it comes to asset returns, specifically for stocks. So that type of process is basically, examine whether, whether the volatility of the asset is going to be stochastic.
The assets are not stationary, so we usually
the asset price is not stationary in general, but the returns are sometimes. Yeah.
Yeah, that's true. So when we have negative returns, we can use it.
Sure, because that refers to not again. So keep in mind, this doesn't refer to the. If YT is used for returns, this is what you see here. This thing is going to be its conditional variance. Okay, that is going to be its conditional variance, and the conditional variance cannot be negative, by the way. So these parameters, and that is a restriction what you'll have. Okay, so again, I will use the sum notation to denote this. These parameters are non-negative. In particular, the first one is always going to be a positive one. That must be greater than 0. If these are 0, which means that this is disappearing, right? Then the conditional variance is a constant, by the way, in addition. So that captures also that type of process where you have a constant conditional variance. And that is simply just a noise with the variance alpha squared. You understand what I'm saying? Okay, so if you take that, if this is the process, then the variance of that is simply just going to be alpha squared, which means that the process alpha 0 squared, sorry. So this means that the process will would behave just like a noise. You understand? And nothing else. It's uncorrelated, and its expectation is 0, and it has a constant variance there. Got that? Okay, so that, because, you know, this expression will not have. But this is what the conditional variance of the process will look like. So therefore the name is common. I mean, therefore the name. Conditional heteroscedasticity means literally that the conditional variance has some time-dependent issue. It's not just a time-dependent, because it could be also deterministic, but it's also stochastic as well. You understand? Because Y is a stochastic process. So the past observations are stochastic, let's say, if you don't have the observations at a current point of time, which is capital T then, and that is how it's going to be. Okay, so that is used typically for capturing the dynamics of adverse returns. And this is, just to be honest, this is what your next assignment is going to be about. I want to know, I mean, you choose an asset class, and you take the returns, and you examine whether these returns exhibit some sort of Arch-Garch effects, which means that whether it has some sort of volatility issues regarding, you know, time dependency of the volatility. All right? Or, to be honest, it's basically the conditional variance. But I'm going to consider that issue later on. But that's what it is. Okay? So these are the so-called, this is a very famous type of processes. That explains a lot of things. When you remember, I'm not sure which area you would come from, but if you come from the finance area, remember the Black and Scholes model, right? There were a lot of issues regarding the Black and Scholes model. One of them is basically the volatility is not a constant, and there is some sort of, you know, the smile effect, you know, that type of thing. Okay, so that is due to the fact that returns have excessive kurtosis, for example, okay, which cannot be explained by that model. So, but it can be explained by stochastic volatility type of processes, right? So that has basically generated a lot of attention, these things, both in economics as well as in finance, but in particular in finance. So I want to basically focus on that one rather. All right? Okay, so this is a very famous type of process. In the original slides, I also put down the paper, the reference, so you can quote it if you like, okay, when you do things like that. There is a lot of extensions to these processes, but I'm not going to focus on that one. I'm going to just generalize first the properties of that model before I continue. So what are the properties? Now, again, it has every single property that the stochastic volatility model would have. So it means conditional mean is 0, unconditional mean is 0. The unconditional variance is equal to the expectation of sigma squared, and the process is going to be not autocorrelated. But keep in mind, guys, just because it's not autocorrelated, it doesn't mean that it's not going to be, there is no dependency structure, because as you might guess, okay, so that sounds counterintuitive, which I admit, there is dependency structure, right, which is involved. So if you put that inside here, you know, current observations do depend on past observations. So why would you basically assume that the process is not autocorrelated? Okay, now it is going to be autocorrelated because there is no linear relationship between current observation of the process and, let's say, future observation or past observation of the process. But there is going to be some sort of another type of relationship which you actually see here. So keep that in mind. There is no autocorrelation, believe it or not, okay? But there is going to be dependency. So I just want to emphasize there is going to be dependency, serial dependency in general, depending on, of course, the parameters, but there's going to be one in general. Okay? Okay, so that's a very important issue. And then you need to understand that the same thing is true for Arch-Garch type of processes when it comes to stationarity. You would only look at the variance. Okay, so if this thing does not depend on time, then the process is going to be stationary, because everything else that is required for the weak sense stationarity is automatically satisfied. All right, guys, is it clear? So I'm focusing on the variance exclusively. This allows me to bypass everything else. Okay, so since that type of process falls under the category of the stochastic volatility type of process that I defined at the beginning of this lecture, every property that this process has will also apply to the Arch type of processes, But in addition, and I wanted to basically mention that one, the conditional variance, and that's what I'm talking about. The conditional variance is going to be time dependent no matter what. All right? I mean, in general, let's say, if these parameters are not zero, that are involved, you know, the alpha 1 to alpha q is not zero, then there is going to be some sort of time dependency that is involved. And not just that, but in addition, it's going to be also stochastic as well. Okay, not just, let's say, a deterministic trend when it comes to the conditional variance of the process, but also basically some sort of, let's say, stochastic conditional variance, okay, because that is going to be a stochastic process, okay? All right, so that is interesting. So no matter what, even the process is stationary, guys. So that's what I'm trying to explain here. This is a very important note, by the way. So the conditional variance is going to be time dependent no matter what, even the process is stationary. But keep in mind, guys, for stationarity does not require the conditional variance to be time independent. It only requires the unconditional variance to be time independent. You understand what I'm saying? So the unconditional variance, which I'm basically calling it here, is going to be the expectation of the square of sigma. That is true. Whether this thing is time dependent or not, that will decide whether the process is stationary. Okay? But keep in mind, guys, this is a very important issue. Stationarity does not require the conditional variance to be time independent. Okay? It sounds counterintuitive because people think that conditional variances are some sort of a weaker concept than unconditional ones. But in that regard, this is not true, even though the conditional variance, okay, the conditional one, can be a stochastic process, but the unconditional one cannot. Okay? That is not possible. Okay, so that is always going to be a constant. By the way, and I assume that it is finite, right? Because that falls under the category. But in particular for arch-gauge type of processes, this is going to be finite. At least, you know, I mean, because that is referring to the expectation of the process. All right, guys, so that's a very important issue. And yeah, so we're going to basically discuss this. So this is what conditional heteroscedasticity is referring to. Conditional heteroscedasticity means, again, that the conditional variance of a process has some sort of time dependency. Okay? In particular, in this case, it is going to be stochastic in addition to that. And it is autoregressive. Why? Because the conditional variance equals, and that's what you're going to see, you know, this type of autoregressive structure where the squares of the process itself are involved. So keep in mind, guys, these are the past observation of the squares of the process y itself. Okay? And that is where the term autoregressive would come from. Okay? So that has an autoregressive structure, not for itself, but for the squares of the process. Do you understand that name, guys? So where the name autoregressive conditional heteroscedasticity would come from. Autoregressive means that it depends on its path. In particular here in this case, it depends on the squares of its path. All right? That is, you know, obvious. Okay, so this is what it is, right? So we'll have, so, and then, but still we have uncorrelatedness, right? Okay, so that sounds counterintuitive, but I will address that issue later on. Anyways, now I'm going to show you that the conditional variance is indeed this expression first, okay? So when it comes to these arch type of processes, which are listed above. Okay, so I'm going to put them here above. This is the structure, what it be. Q is the order, right? I forgot to say that. Q is the order of the autoregressive structure of the conditional variance. So again, keep in mind, this is equal to the conditional variance. So if I say conditional variance, I mean this expression in particular. All right? Now, I'm going to show you that this is equal. This is relatively easy. So, of course, the variance of the process is equal, the conditional variance is equal to its conditional expectation of the squares. Why? Because the conditional mean is 0. So minus, that would be the case minus the conditional mean, okay, but the conditional mean, since this is the square of the conditional mean, sorry, but the condition, since the conditional mean is 0 of the process, so you could basically just neglect this. And the current observation of the noise doesn't depend on anything, so the expectation of the products is going to be the product of the expectations. That's not difficult to see. Now, in addition, you can take out sigma squared from the expectation operator this time. Why? Okay, so I'm going to show you, I mean, again, I will address it. So you can simply take it out. Why? Because as you see, and I want to show you that one, so sigma squared depends on the past of yt. And the past of yt is here. And it's completely given by the past of yt. So if you know what the past of yt is, so given the past, then you know what sigma squared is or was. So then you can simply just take it out from the expectation operator because there is no randomness involved anymore. You understand what I'm saying? So if you know the past, then it is a constant. And if you know, if it is a constant, there is simply just a linear transformation involved, and then you can simply just take it out from the expectation operator. Do you guys get that? Okay? So again, therefore, again, so conditional expectations and conditional variances are actually a very powerful tool, by the way, okay? Because it allows you to take out things from the expectation operator if these things are given. So consider the past, which is given. So if this is given, and this is given, and if this is given, then that will be given. So then you can take it out from the expectation operator because the expectation of a linear transformation is simply a linear transformation of the expectation, guys. You understand what I'm saying? So, yeah, and that is equal to 1, so that this will be the result. That is the conditional variance of the process. And that can be time dependent because there is t involved. Okay, so there is basically structure of time there involved. Now, in addition, it is going to be stochastic because it's up here. But that's just a side note. All right? Is it clear, guys? So that is a very important issue. And no matter what, even a process is stationary, its conditional variance can be time dependent. Okay? It can depend on basically the path of the process. Okay? And that is actually true when it comes to volatility clustering, for example, this phenomena, because if, let's say, asset volatilities tend to be large, okay, then it also is going to be true, or the tendency is going to be true for the following future observation. But I'm going to talk about that later on. Now, let me explain when the process is stationary. The process is going to be stationary if and only if, I mean, it has to do something with the variance, of course, right? So I will focus on the variance of the process exclusively, nothing else. And it is going to be stationary if and only if the sum of these parameters, these alphas, keep in mind, I'm just talking about these alphas. Alpha 0 is excluded from the consideration. That is important, okay? So alpha 0 is not part of this sum. The process is going to be stationary if this sum, where again alpha 0 is excluded, is strictly less than 1. This is it. And that will be it. Okay, so there is this condition. Okay, so that is basically what we're going to look at. Now this is equivalent of saying that 1 minus the sum of these parameters is greater than 0. That's the same thing. So keep in mind, I mean, of course, you subtract that, but this is equal to 1 minus the sum of these alphas, obviously, and 1 minus the sum of these alphas being greater than 0 is equivalent of saying that the sum of these alphas is less than 1. This is the stationarity condition for Arch processes, and I'm going to illustrate that. So if this is true, then the process is stationary. If the process is stationary, then this is true. Yes?
Is it possible that the data is stationary in the level up?
Excuse me?
Is it possible that
Yeah,
the data...
sure. If it's stationary, then it's also going to be asymptotically stationary.
So when data is stationary, the model is also stationary?
Sure.
Okay, so we can either check stationarity like this after estimation
Yes.
or running the
I mean, okay, you need to test this. So keep in mind, these are the true parameters. But in practice, when it comes to data analysis and you need to estimate these coefficients. But your estimates can deviate from their true values. I mean, of course they do. Okay, so you need to test this. But that's going to be basically the corresponding hypothesis. So the null hypothesis is involved, is referring to the restriction that the sum of these parameters is going to be equal to 1. Right?
Instead of this, we can just do the ADF test for the data?
No. This is not, I mean, of course, first you do that, but again, this is a different type of procedure. Yes, you would test that, for sure. Okay? But that has a direct impact. So you can do the ADF test first. Sure. Okay? But I mean, when it comes to the estimation, that's what you're going to have. This is not the way to test estimation, as I mentioned before. That would be the null hypothesis here. Because the issue is we don't know the distribution of the F statistic under the null hypothesis, but we do know when it comes to the so-called, you mentioned this before, the augmented Dickey-Fuller test. But I'm going to discuss it next week, not now, next week. So you don't need to test this. Keep in mind, this is a theoretical consideration because in practice, you don't have access to these parameters in general. You only have access to those estimates. So you only have alpha 1 hat, alpha 2 hat, and so on, and alpha q hat maybe, okay? But these things, okay, these things are not necessarily equal to their theoretical counterparts, okay? So that is a theoretical consideration, by the way, theoretically speaking. Do you understand that, guys? Okay, is that clear? All right, so yeah, and of course, basically, if it's stationary, and I wanted to add this, if it's stationary, then its variance is going to look like this. And you might see basically why these things must be true. I mean, number one, it must be true that alpha 0 is greater than 0, is greater than 0, strictly speaking. Because if it is 0, then there is no variance, right? And if there is no variance, then there is no process. Okay? That's number one. And number two, this thing is less than 1. Because if it was equal to 1, then you would have a variance which is not finite. So then it would be not stationary. You understand what I'm saying? Okay? So that is basically allowing you to consider the other case, what happens if the sum is equal to 1 or even greater than that. Now, if it's greater than that, it doesn't work either. Okay? I mean, technically speaking, the variance will be negative, so that doesn't work. But if it's equal to 1, then you would have a variance which is not finite then, in contradiction to a stationary process. Okay? All right? This is called the I-Gorch type. You know, so there is also some sort of integration order involved if the process is not stationary most of the time. Most of the time. I'm not saying all the time, but most of the time. Is it clear? All right, so this is what it boils down to. Again, I'm considering theoretical concepts here, right? But in practice, the issue is, again, nobody knows what these parameters are. How? Okay, you only know your estimates. Yes?
YT, this is an empirical value. So
excuse me?
YT, this is an empirical
I mean, no, this is a theoretical one. This is a stochastic process. When it comes to that, this is not data, this is a stochastic process. YT is a stochastic process in this case. If you have a sample of the stochastic process that was generated, then it's no longer stochastic anymore. But then still, you don't know these parameters. Okay, nobody knows, again, what these parameters are in practice when you have data observations that were generated from a stochastic process. You can look, you can look at stochastic processes in terms of random variables. Okay, our observations of stochastic processes are actually random variables in this case. You understand? Okay? So in practice, nobody knows what these parameters are. You need to estimate them. And as your sample changes, so do these parameters in general. I mean, just look at the results that I provided you with from the multiple linear regression of an AR2 process, right? I was doing that for everybody so you can check your own results. Okay? As a sample change, so does the estimated. Okay? Right? That is not surprising, by the way. So, but I'm going to basically also do some practical stuff, don't worry. Okay? But I want to back up your applications by the theory. Good. Now, I want to also consider the unconditional variance of the process, since we already know what the unconditional variance, what the unconditional variance is. We don't need to do it again. This is the unconditional variance. You don't need to apply the law of total variance, by the way. I mean, you can, but why would you? Okay, so usually I would do that. What does the law of total variance says? The law of total variance would say that the unconditional variance is equal to the variance of the conditional expectation minus the expectation of the condition, plus the expectation of the conditional variance. Okay, so that is what it's going to be, okay? But that's not what I'm going to look at. Now, okay, here it is. You just simply put it in. Then you see a sum plus a linear transformation of random variables where the expectation operator is involved. Expectation of a sum is the sum of the expectations, and expectation of a linear transformation is a linear transformation of the expectations. So you simply break in with the expectation operator into that structure. That's not difficult, by the way. And the expectation of the squares are equal to their corresponding variances, respectively. Why? Because the unconditional means are 0. So the mean of the squares is equal to the variance of the process. These are theoretical variances, by the way, not empirical ones, theoretical ones. Okay? I was complaining a few days ago about that. In this case, I don't have sample involved. Okay? There is no sample. So, again, these are theoretical considerations. All right, now these are the variances. I'm going to take that. Okay, so everything else is going to be eliminated. I'm going to take that, continue from here, and if the process is stationary, then the variances are equal. Why? Okay, because if the variances are, of course, it's obvious why, because stationarity means, among others, that the variance is time independent. If the variance is time independent, then the variance at the current point of time is equal to the variance of a previous point of time. Is it clear, guys? And every other point of time as well. So since these variances are equal, you can simply just replace them, okay, by the equal counterparts, and then simply solve this equation for the variance of the process, okay? And that's not difficult, by the way. So you can do it just by rearranging it, and that's what you're going to have, all right? So alpha 0 by 1 minus the sum of the remaining parameters, starting at alpha 1. Okay? This is it. So actually, this is not the proof because I wasn't going backwards, but again, let's assume this is not true because, let's say, the sum of these expressions are equal to 1. Now, if the sum of this expression is equal to 1, right, then the variance of the process is going to be it's not going to be finite, obviously, right? So that is a contradiction. So then the process cannot be stationary because it requires the variance to be finite and time independent. All right, guys. So yeah, so if it's not true, then this is what it's going to be. So therefore, that might indicate the other way. All right. If the process is stationary, this is what the variance is. If this is not the variance, then the process is not stationary, period. All right. Okay. Now, I'm going to basically also address different things that are involved in here. Okay, so we're going to address a different type of representation. There is also an equivalency regarding arch and gauge type of processes that I wanted to mention here. So how would you test this? Because to be honest, guys, relatively speaking, arch gauge type of processes are relatively difficult to estimate. So it's not, you need to make assumptions about the distribution of the noise. Usually we assume normality, okay? So then you can do these things with the likelihood estimate. But it's, let's say, not straightforward, okay? Now, if you consider, let's say, another random variable, which I'm defining as E, okay? And E is going to be the square of the current observation of the process minus its conditional variance. So I'm simply just subtracting the conditional variance of the process. Now, this doesn't mean that the conditional variance just simply disappears, okay? But at least the mean of that process, where you have, of course, the expectation of that is simply just the expectation of the whole thing, okay? And the expectation of a difference is going to be equal to the difference of the expectations, by the way. And since this expression, on the other hand, so this expression I'm talking about, that one, is equal to the variance of the process, and the variance of the process is equal to, basically, to the expectation of sigma squared, this thing is going to be 0. All right? That is obvious. So you can consider that to be some sort of a noise. Now, it's not a noise because it's not necessarily not necessarily uncorrelated. It could be correlated, by the way, okay, depending on basically how you were looking at it. And the variance is also, let's say, more or less at least problematic. Okay, it's not going to be a constant one. But again, I could look at that from this perspective still, okay, because at least, you know, if I rearrange that process, so I'm going to start off here, and what I'm going to do then is I'm going to substitute, all right? So I'm going to substitute basically sigma t by the following expression. So sigma t squared is equal to, and that's what you see, yt squared minus epsilon t squared. I call this a pseudo noise, okay? So let's call that the pseudo noise, okay? At least it has an expectation 0, at least, okay? So it evens it out, all right? Anyways, but again, so if you substitute, then you're going to, and rearrange the whole thing, you're going to find a autoregressive structure for the squares. Keep in mind, this is basically an AR process of the squares. So what you see here, okay, an AR processor for the cube, by the way. If you, let's say, consider that one to be a pseudo noise, okay? Now this means that an arch-gauge type of processes, okay, imply, and that's an important issue, an autoregressive structure regarding the squares of the process. That's an important one, okay? So this means that there is a dependency of current observations of the process and their past observations, but not a linear one. You understand? Okay? A square one. So, how would you detect basically arch and gauge effects? It's simple. I mean, according to this procedure. It's not a procedure, guys. It's an illustration. You simply estimate, or you try to estimate, an AR process for the squares, not for the original observations, for the squares. And then if there is significance with respect to that issue, okay, so you can do the F-test, by the way, so you find basically the explanatory variables to be significant. So if, meaning that if the squares are autocorrelated, this indicates arch effects in the data, okay, stochastic volatility in the data, if there is an autoregressive structure for the squares of a process. And that's something that you can do, by the way, for your next assignment. So you can simply take the returns as they are, square them, trying to estimate an AR type of process. You can use ARMA, by the way, okay? And if this model is significant, let's say at the 5% level, you can argue that there is significant conditional heteroscedasticity, basically, for the process itself, at least at the 5% level. You understand that? So that's simple. Again, so this boils down from this illustration. So again, an arch process implies an autoregressive process for the squares. And you can go backwards. If this is not true, then that is probably not true either, at least from the empirical perspective. You understand that, guys? Okay? So this is how you can detect. I mean, I'm not saying that's the only way. And you need to be a little bit careful, because these parameters that you'll have being estimated from the squares of the observations from the process that you have, for example, the squares of the returns are not going to be the same as the parameters that, you know, the arch process would generate for you, okay? But that's just basically an indication for that. You understand what I'm saying? So if there is significance for these of these parameters, or let's say of the model itself, then you could argue, or that might be considered as a proof, at least from the empirical perspective, that there is arch effects in the data, meaning that volatility is conditionally heteroscedastic. You understand what I'm saying? Okay, so that is an important issue, and that's how you can detect it based on this representation, which is a relatively simple one, to be honest. But a good approach is always, at least in my estimation, also a simple one. Does that make sense, guys? Okay. So again, I will summarize this later on. Okay, so squares of the arch processes are autocorrelated. Therefore, you cannot say that the process is serially independent. Okay? This is also the case for the MDS type of processes. You might remember those. Martingale difference sequence, same thing. Serially uncorrelated, but not necessarily serially independent. Okay, that relates to that, by the way. Okay, and that also models some changes, right? Martingale difference sequence, difference have something to do with changes or increments. And increments have something to do with returns also. Is it clear, guys? Okay, so yeah. That's what I will try to mention here. Okay, and that's the approach to test this, or one of the approaches that you could test this. Of course, the other one is estimating the model directly. But again, it's relatively difficult. Okay, we want to know basically whether there is arch-gauge effects involved. Not necessarily how they look like. Okay, maybe due to response analysis that would be important, but that's basically first off, you know, establishing that fact. I mean, empirical issue, let's say. It's not necessarily a fact. Anyways, so I mentioned before volatility clustering, and that is where, you know, arch type of processes are involved. So large changes in, let's say, in return of an asset tend to be followed by large changes, let's say, the next day. I'm not saying it is, but this means, I mean, and the other way around, small changes tend to be followed by small ones, and large changes tend to be followed by large ones. So there is periods with large volatilities, and there is periods with small ones, okay? But that is just a tendency, guys, so it's not necessarily true. I was basically showing you a sample here of an arch process. This is an arch 1 process, by the way. Okay, that's how it would look like, and the squares look like this. So if the squares look like this, okay, you have this type of volatility clusters involved, okay? And this could be regarded as an indication for stochastic volatility, at least conditionally speaking. You understand? Okay, so this is basically, I mean, you could not see this directly here from the process itself, unfortunately, but you can see it from its squares, right? So that indicates basically an arch type of process if it is looking like this. So this is what actually volatility clustering is. All right? Again, it changes basically, by the way, if you change your parameters. So I was using the same noises, but keep in mind you have a different scale. So the level of scale would change, okay? And volatility clustering becomes visible if this are more visible, let's say if this parameter would change. So again, keep in mind the scales is different, very much different. So, okay, so these are the clusters that you see, okay? And again, if you see something like this in your diagram, this might be an indicator for arch effects in the data, meaning that the conditional variance of the process has some time dependency, okay? Conditional variance, okay? Large changes generate large changes. That's a tendency, at least. And small ones tend to generate small ones. Okay? So sometimes, of course, it's going to be boiled down, these things, all right? So these are also clusters, right? Nothing really happens, but maybe after a while, everybody freaks out, And this allows you to basically to predict volatility much better than some sort of standard type model. And so again, I would like you to consider that one in your next assignment, by the way. So you can choose any data you like of an asset's return. Preferably people use stock market indices that you can. Okay, so it's open to the public. Use daily observations if I may ask, okay? And that is what your next assignment is going to be. You need to test whether you'll find arch effects in the returns of, let's say, your period of interest. Okay, the more interesting this is, the better. It might be relevant when it comes to, let's say, a financial crisis. Okay, so let's say around 2007, 2008 or so, it might be an interesting point of time, and maybe you can do, again, so I'll let you do whatever you want to do, and if you illustrate your relevance of your, let's say, economic ladder sufficiently, this is what it's, what this will be, okay? So again, it's more or less also important how you sell the relevance of your topic. This is a very important issue. I'm going to give you credit for that. So if you do it sufficiently, then this is how it's going to be. All right, but again, I'm going to talk about that later on. How would you test this? Now, there is one alternative, a simple one. Again, this is not the only one. You can simply just estimate the model and test its significance, right? Significance of the parameters, and so on. Yeah, but there is that's a simple approach. So based on the fact that, again, arch models implies autoregressive models of the squares. Okay, let me tell you this. This can be also extended to, let's say, the Armo type. So if returns, the squares of returns exhibit some sort of Armo type model, okay, then the original process would be the so-called generalized version. Okay, we're going to talk about that next week. So this is basically the relationship. Okay, so if you have also moving average structure for the squares, okay, of the process involved, that this relates to the generalized version of the arch model, which is called Garch model. That came out 6 years later, if I recall it correctly. I'm not sure, 1986 or so. Yeah, but that's, what you will have. So you can take that as well, but you don't need to, okay? Because again, just as, allowing basically Armo structure, moving average structure for past shocks, to get smaller models actually, this is just doesn't change the fact that, you have arch effects in the data. So it will not make a big difference because you don't need to specify the structure. I only want to know, are there any effects? Not necessarily how they look like. Okay, so you don't need to implement that, but you can, of course. So you can choose basically implementation instead and test its significance. But you probably won't understand what the process does. Okay, so I'm always kind of struggling with these things because you can say, okay, download this package and then, estimate your arch model, but nobody actually is knowing because you don't use OLS for that, for sure, right? So you have a different type of estimation procedure involved. But again, it doesn't matter. So you can do that if you don't want to follow this approach. But you can, that's relatively easy to see. So already, if you just, square the data and yet you're suspicious of, having arch effects, and just look at the diagram, and if it kind of looks like those that I was showing you, that might be an indicator for arch effects. But I'm not saying this is a proof. Okay, so again, where to draw the line is difficult to see. Okay, so you cannot draw the line. Again, from a perspective, nobody knows what the true models are that generating these observations. Okay, nobody told me, so again, nobody's telling you either. So again, estimate the squares, or estimate an AR process for the squares. You can select basically Q with information criteria. Okay, so you can use that one. Okay, how large the model should be. This is also a hint for your, I mean, for this assignment, by the way, okay, that you are working on, and the following one as well. And yeah, so this is basically, you know, what you can do. Now, you perform an F-test on the model. The F-test basically jointly tests the null hypothesis at every single coefficient that is involved here is 0, because if that's the case, then there is no stochastic effect regarding the volatility. So then it's going to be the conditional volatility, the conditional variance is going to be simply just a constant if these parameters are 0, right? No time dependency regarding the conditional variance of the process. That's a null hypothesis, by the way. And yeah, and if you reject this, then of course, if you reject it, okay, so then you consider to be having significant arch effects, at least at the 5% level. So if you reject the null hypothesis at the 5% level, then you would simply just, you know, assume that that arch effects are present at the 5% level, by the way. And that should be fine. Okay, so again, this is your next assignment, by the way, which again I wanted to talk about. So this is here. And yeah, and the background is, of course, you know, I mean, you have these type of models that I mentioned before. Okay, so autoregressive conditional heteroscedasticity models are used, among others, to predict volatility of stocks or other asset returns. All right, so I mean, for asset returns in particular, so not the prices, but the returns, right? And forecasting volatility is of great importance, right? Of course, managing risk sufficiently, and that's not a surprise, okay? Now, the issue is, of course, model selection. This boils down also to the model selection that we were looking at yesterday, okay? So you can use that one also, because if you have the wrong model, you probably get the wrong forecast too, okay? So selecting correct model is going to be important. And then you would need to examine, of course, the structure of the data, so whether there is actually stochastic volatility involved or not, at least conditionally speaking. You understand? So that's what I'm going to, or you will have to look at. Okay, so I would like you to ask you to estimate a model. It's basically, I mean, it's a univariate case, but it's not, if you like to do it in a multivariate case, you're welcome to do, but I wasn't talking about that, so you can have these extensions if you like. I'm not going to be worrying about, but first off, I mean, you can just simply use a univariate model. Most of the time, stock market indices or examine arch gotcha effects, but I want to be more specific, guys. Stock market returns, or returns of stock market indices. So I'm talking about the returns, not the prices or not the indices themselves. Okay? So that's what you would need to look at. So first off, you would need to calculate those. Okay? I mean, if you use daily observations, you would use the log returns, okay, because these are the differences of the logarithm of the process. Okay, so if you have, let's say, the prices, let's say S denotes the stock price, then this is how you calculate the log returns, right? The differences of their logarithms. Anyway, you might know this from the Black-Scholes formula. Okay, or Ito's lemma. Does it tell something to you? Okay, I'm not sure. Anyway, okay, so yeah, and the squares of the series can be used to test arch effects, as I mentioned before. You can do that. You don't have to. You can also use packages, of software packages of Python. Somebody using Python, I'm not sure who it was, but somebody clearly using Python. I was recognized from your submissions. But you can, so you basically you can do that. Okay, so maybe you can Google like how to estimate an arch model using Python, and you can, and you could simply just test the significance. I wanted to have stationarity, so please use the returns, not the price, not the stocks themselves, the returns. Okay, I want to be more specific. Okay, so you would need to calculate those, and yeah, present your results briefly, 2 to 3 pages max, okay, not more, Okay, so that's going to be short one. Short little paper, okay, which I like, so you can do that. Present your results, please, briefly. And you don't need to do a literature review, but I wanted to have some references in your introduction. Okay? So in the introduction, okay, illustrate that in introduction, okay? So when you use the introduction, you need to sell your paper. This is always a requirement. And if you want to sell it, you need to illustrate its reference by using the scientific literature. Okay, so you would need to drop, let's say, one or two, at least one or two, maybe 3 papers, maybe more, but not more than 5 or 6 maybe. So not more than 6 papers in the introduction to illustrate the relevance of your work. Because the question would be, why? Okay, so why are artifacts relevant? Okay, and you need to justify that. Okay, now the better you do that, okay, the better your work is going to be. And if you also tell me why you choose this asset, why not another one, why you choose this period and not another one, then it's even better. Okay, so it matters, the justification, guys. This is crucial. Okay, so again, I'm completely open, so maybe you can look up the literature yourself, what the other people do, and try to copy that. So you can say, okay, I'm following the approach of X, Y, and Z. And then it's going to be very hard for me to criticize it. Simple as. Okay, but you do it differently because you would say, okay, these guys were estimating the models directly. I'm going to estimate the square or I'm going to estimate an AR process for the squares of the returns and see what's happening. In addition to the work these guys had done. Do you get that? Okay, so again, it's going to be always very important how you illustrate the relevance of your work. Why should I read your paper? Okay, I mean, okay, to be honest, I'm reading it because I got paid for it, that I'm reading it. But that's not the only issue, you know what I'm saying? So I would basically interested in, you know, having other reasons than that. Okay? I mean, to be honest, guys, if you don't pay for the music, there is no music. You understand what I'm saying? So, and that's the same thing. Okay? If you don't pay your teachers, there is no teaching. You know? So, I mean, I like to do this job. I'm doing it for fun, but again, it's this is how it comes. Anyways, okay, I'm putting on YouTube, so you can watch it there if you like. Okay, try to justify it. Okay, and if I say your model, I mean maybe the data might be interesting to look in that. Maybe the time frame that you use. Why this time frame? Again, comes down to crises. Okay, so that could be interesting. Or maybe some let's say time frames where everything is quiet. Okay, that could be also the issue. Anyway, so try to basically justify it sufficiently. The better you do it, the better it becomes. Okay, so that's not just about you explaining, okay, I was estimating that, I used this information criteria, this is what comes out. Then you conclude there is gauge effects or artifacts in the data at the 5% level. Okay, I'm fine. But why? Okay, so why is this important? Okay, I mentioned basically I mean, you don't need to forecast things, so that's not what you're doing. But I would like you to identify these effects, whether they are present or not, let's say from the empirical perspective. That should be fine for a little work. Okay, so let's say an assignment of, let's say 10 days, you know? Okay, and I want to basically, now, somebody asked me to basically you can do that basically with somebody else. I'm allowing you to do that. But then, of course, you need to write a little bit more. So there is synergy, okay, when you work with somebody else. So let's say if there is one person, then maybe you write, let's say, 2 to 3 pages, okay? And if there is 2 people, okay, maybe you write, let's say, 3 to 4, okay? Or 4 to 5, okay, because you need to find your common denominator. So allow two people to work together in this case, not just working together, but literally speaking. So you can have a co-author for that. But then you, of course, I'm expecting more. So if you don't provide me more, then it might not be sufficient. All right? Okay? It's not just, I mean, of course, it's the quality that is important, obviously. That is more important than the quantity, okay? But if you go to a restaurant and you come out hungry, that's not a good one, okay? You understand what I'm saying? So that should be also an issue, okay? So allow two people to work together if you want, okay? But please put your names, both of you, each of you, I mean, of course, on the paper so I know that you're writing it together. And you need to submit anyway. So please do not just submit for somebody else that has editing reasons, okay? Because it's very difficult for me to, I mean, I have so many files that I'm getting from you that it's very difficult for me to put that in the right structure and to organize it. So please, so because if you, let's say your co-author doesn't submit, then if I'm looking at your data, okay, so the files that you send me, okay, where is this assignment missing? Okay, that's my first question. And who was the co-author? And I couldn't figure it out who that was because I don't remember. You understand, guys? So please, both of you should submit, even if you have the same paper. Yeah?
So in the name of the title, we are supposed to also state...
Yes, both authors, please. But not more than two. Okay, so not more than two people in a group. 3 is too large. So if there is 3 people, you know, working together, there is always one people who's causing some trouble. And one person who's basically causing some trouble. I have an experience where basically 2 guys were working with a girl, and the guys were more interested in the girl than the paper, you know. So that was an issue. And they tried to approach her, and she rejected it. And these guys got upset, okay, so they tried to, you know, tease her in that sense, you know. I mean, I don't know, try to boycott her or whatever. So, and then she texted me like 2 days before, okay. So guys, just for you to understand, I'm not your psychologist. You know what I'm saying? So I could do these things, I can take care of these things, but I don't want to, okay. I'm not qualified for that. So I have a couch, but this is not what it is built for. You understand what I'm saying? So I don't want to do these type of things. Okay. I mean, I don't know these guys, you know, to be honest, what they were thinking. But again, that's just, that's not my business, you know. They were trying to approach her at the same time. Anyways, she rejected both. So, and they got upset. You know what I'm saying? So anyways, so that was the issue. So since then, I said no more 3 people. 2, it's fine, okay? But not more than 2, all right? Okay, so, yeah, probably these guys were gangbangers. I'm not sure. Anyways, okay? Not my business, but I don't want to solve issues related to that. Anyways, okay, guys, so that's your new assignment. Of course, the deadline is going to be next Friday. So, yeah, I try to finish 4. I'm about to release the results of assignment 4, 5 maybe on Friday. And so then I can do assignment number 6, basically your solutions on Sunday. Yes?
Yeah, you said when we estimate the AR process for these squares, you can't use the ONS?
You can, sure.
Okay.
Sure, yeah. So this is a standard approach. It's a very easy one. But you need to find the order of the model, right? So that is an issue. If I say, you know, when it comes to, so you need to estimate basically the order, what the order would be, okay? So you can adopt, let's say, information criteria to find the lag order that is involved, okay? So that's always also breaks down to how you justify that, okay? But again, so I'm letting you do it. Okay, so this is not, there is no way to general approach related to this, so unfortunately. So, but you need to, maybe you can check out what other people have done in this area that you're looking at. And you can say, okay, I was following X, Y, and Z. Then it's going to be very hard for me to criticize it within a seminar. Okay? And there is 29 people, so I don't have even time for that to look everything up in detail and criticize it. But that doesn't mean that you should not be careful. Okay? All right? Okay, guys. Yeah, that was it for today. And see you next week. Take care. Thanks.